Dear students and participants of the course on railway engineering, today we are going to extend our discussion on LWR and CWR. If you remember, in the previous lecture towards the end, we were discussing about this long welded rails and the continuous welded rails. And there we talked about the locations where these type of rails can be used or even they should not be used. Along with that, we have also talked about the track structure which should be provided, and when we say track structure, it means we are talking about the ballast, the rail section, type of sleepers, etc., which should be used as a part of it. Before that, we also discussed about the wear in the rails, and we talked about the precautions which should be taken against the wear and the permissible limits which are allowed for the wear, and beyond that, if it happens, then there is replacement of that rail section. Now let us continue with our discussion on LWR and CWR. Today in this lecture, we will be discussing the provision of these LWR and CWR on bridges. We will talk about the thermal forces which get induced. If you remember, we discussed about this in the previous lecture too, and there we said that towards the end there is some length which is going to move because of the change in temperature, and that particular length here we will be discussing as breathing length. Then we will go to the consolidation of track, the ballast resistances will be talked, and finally the hysteresis phenomena will be taken up. So let us start the provision of LWR or CWR on bridges. Now wherever these LWR and CWRs are provided, they can be continued over the bridges. The bridges which have been provided with the ballasted deck without bearings like slabs, box culverts and arches, these are some of the locations where these LWR or CWR can be continued. In the previous lecture, we did talk about that when we are talking about these type of provisions, there are certain distances which needs to be maintained, and the distances also need to be maintained in the case of SEGs which are providing as a part of the track. Now detailed calculations are required if the LWR is provided on bridges with ballasted deck with bearings. If ballasted deck with bearings is being used, that means now here we are talking about the bigger bridges, the major bridges. In those particular cases, the calculations needs to be done, and those calculations needs to be provided at site also. These are continued on bridges on unballasted tracks provided with the rail free fastenings and the PRC sleeper on approaches up to 50 meters on both sides. That means there is a river, at the top of that a bridge has been constructed and your track is moving at the top of this bridge. So here when we are talking about an unballasted deck and rail free fastenings are provided here along with the PRC sleepers, then up to a distance of 50 meters, say if we say that at this point there is an abutment being provided. So if from this particular abutment for a distance of 50 meters on this side and 50 meters on the other side, we need to continue the things. Now here the maximum overall length of the bridges have been given for the different temperature zone areas and for the two rail sections which usually are used, that is 60 kg per meter and 52 kg per meter. And the two cases with respect to the bridges which are being talked are without box anchored and partly box anchored. So in these cases, the lengths which are being provided, which are being allowed, they are like in the case of temperature zone 1, if you talk about 60 kg per meter rail section, and this is 30 meters, whereas it is 77 meters if it is a part box anchor type. And similarly, if we see from the top to bottom, that is for all the 4 temperature zones, we have talked about the same combination of the 2 types of the rail sections, and there the values are changing. Now here from zone 2, 3 and 4, the values have become constant, say 11 meters for a 60 kg per meter rail, and 27 meter for a 52 kg per meter rail. Whereas previously for a zone 1 it was much higher as compared to these values. Similarly, if talk about the part box anchored system, there the first two cases, that is zone 1 and zone 2, they have different lengths, but when you come to zone 3 and zone 4, then that becomes constant. So, in the case of 60 kg per meter it becomes 23 meters, and for 52 kg per meter it becomes 43 meters. So, these are the changes in terms of the overall length bridges. Then the another case is being given here, where we are talking about in terms of the SEJ, overall length of the bridge, and the initial gap which is provided at a de-stressing temperature, that is TD. So, for the zones, so if you see here, there is one section here and another one. So, 4, 3, 2 and 1, these are the temperature zones which are having the same value of 190 mm as a maximum movement of the SEJ. But for this constant value, there will be overall length of bridges which is going to be different, and it keeps increasing as we move from a value of 55 to 160, that means from temperature zone 4 to temperature zone 1. So, in the previous slide also we have seen that that was the way the values were changing. If we talk about the initial gap which is to be provided at a de-stressing temperature of the rail, then these values are like here 7 mm for zone 3 and zone 4 and 6.5 mm for zone 1 and zone 2. But if this maximum movement of the SEJ is 120 mm, then that is related only for two zones, that is 1 and 2 zone. And in this case, the value of overall length of bridge changes from 20 to 50 from zone 2 to zone 1, whereas the initial gap which is to be provided, that remains a constant value as 4 mm. Now, another thing is, if the girder bridge is provided with SEJ at the far end approach of the bridge, that is 15 meter away, using rail free fastenings with PRC sleepers. So, whenever the bridge is being provided, you are talking about LWR, CWR, then we need to see that what is the location where this SEJ is going to be provided. Another thing which we can see here is with respect to this 120 mm of the maximum movement of SEJ. And instead of providing this 120 mm of this movement, what can be done is that two gaps of 65 mm each maximum can be used instead of this IRS design SEJ with 120 mm gap. So, this is a change which can be done, it is better to use in that form. Now, these welded rails, they may be provided from pair to pair with rail free fastenings and with SEJ on each pair. So, you are having a big bridge in this form. So, this is being supported. So, initially as we said that there may be a abutment, but then there are other supports which are provided because this is a long bridge. So, this LWR, what it says is that welded rails may be provided from one pair to another pair along with the rail free fastenings, and SEJ will be coming at this location. So, this is the way it can be done. Now, welded rails may be provided over a single span bridge with rail free fastenings and SEJs with 150 mm gap at 30 meter away from both of the abutments. So, here when we say that this is the abutments, from here we are talking about a distance of 30 meters at that location, means up to this we are going to provide this in a case of single span bridge. The rail shall be box anchored on 4 sleepers at the fixed end of the girder, if the girder is supported on rollers on one end, rockers on the other side. So, this is a condition how the girder is being supported. At one side there is a roller and other side it is a rocker. So, in that case it shall be box anchored on 4 sleepers. In case of the girder which is supported on the sliding bearings on both the sides, then the central portion of the welded rails over each span shall be box anchored on 4 sleepers. So, some changes are there with respect to that what is the way the bridge has been provided. Even if it is being provided with the girder system, then in that case also what type of bearings are being provided will define that where something is to be done. But in both of those cases the box anchoring on 4 sleeper is common. The bridges on which LWR CWR is not permitted or provided as per the above conditions, they shall be isolated by a minimum length of 30 meters of well anchored PSC sleeper tracks on either side. So, this is also another condition. The approach track up to 50 meter on both sides shall be well anchored by PRC sleepers with elastic rail clips with minimum tow load. So, this is all in combination with each other as we have discussed previously. There were one case of 130 meters, in previous cases we talked about the 50 meters. So, those together are being taken up in these 2-3 slides. Here one such situation has been shown to you. Say if the first one at the top, it is a welded rail on girder bridge. So, what you can see is that there are piers being provided, and these piers which were provided here, then the SEJ is coming at the top of it, the LWR is moving from one pier to another pier, and then on the side if you see the girders are being provided. So, if the girder is provided here, then that is also being supported on these piers, and there will be a tongue rail which shall be in continuation to the free end of the girder. 4 sleepers box anchored at the center of the span is being done here. So, this is the way all of the things are going to meet combined. So, here also what you can see is there is a 4 sleepers box anchored at the fixed end. So, what this is the fixed end, this is the end finally, and the bridge is moving in this direction. Again there will be a fixed end on this side. So, at the fixed end again, just beyond the fixed end at a certain distance we have SEJ which we discussed, can be 30 meters or more, and here the 4 box anchored sleepers are being provided at this particular location. If you look at the another one which is shown at the bottom, here in this case there is a LWR or CWR on a girder bridge with SEJ at the far end approach of the bridge. So, what again you can see, the abutment is here, 15 meters ahead of it is an SEJ being provided. Then this LWR is moving from one pier to another pier. So, that is you can see it is being supported at this location, and finally it is going back to the fixed condition on the other side at the abutment. So, that is a provision which is being done. So, here if we try to see that these one being shown in this form, they are the roller bearing, this one is a sliding bearing, and similarly here also this is a sliding bearing, whereas this is a roller bearing here, and this triangular one is a rocker bearing. So, this is an arrangement which we just talked about in the previous slides. Now, temperature zones, how they have been defined and what are the values which are going to be there, let us look at one by one those things. The very first thing which we are discussing here is the maximum length of the single span bridge, because this is the another point which we have discussed. So, here again if you move from zone 1 to zone 4, then the length is reducing, it is 146 meters in the case of zone 1, whereas it is only 75 meters in the case of zone 4. Now, when we are talking about these temperature zones, we are talking about the rail temperature. So far we have said that there can be a rail temperature which is defined by TD, there is a rail temperature being defined by say TP, or there is a rail temperature defined by TM. So, there are different type of such notations has been used. So, we need to talk about this also. Now, here what we are talking is first of all how the temperature is measured. There are different ways in which it can be done. The first one is an embedded type thermometer. Now, this embedded type thermometer is shown here on the right hand side. One of the diagram is being depicted, wherein there is a long arm which can read up to 100 degrees centigrades. There is a seal at the bottom, there is an MS clamp and there is a piece of the rail head, and in that there is mercury bath. So, as the temperature changes, this mercury will start changing. So, it is inserted in a cavity which is filled with mercury and it is then sealed. Within 25 to 30 minutes we will get the temperature of the rail. So, it means it takes long time here, 25 to 30 minutes, so as to give you the temperature. The another one is a continuous recording type thermometer. It is being shown how this is done. So, let us understand what it is. It has a graduated chart. So, this is a graduated chart mounted on a disc which gets rotated by a winding mechanism at a constant speed to complete one revolution in 24 hours or 7 days. Any of the settings can be there. So, this particular disc is going to rotate, and at the same time there is a recording pen on the top here, and it is being connected through a capillary tube to a sensing element, and this sensing element we are going to connect with the rail. So, the sensing element is attached to the web of the rail and it is connected to the recording pen through a capillary tube which is filled with mercury. So, here in this capillary tube the mercury is being filled. The sensing element is now being attached to the web of the rail section. So, whatever temperature is changing, slowly this effect will come here and then accordingly this will give you the value. The third type is a dial type of a thermometer. So, again this is being shown in the diagram on the right hand side. This is bimetallic type which is being provided with the magnet and it is attached to the rail on a shady side, and it takes around 8 minutes to attaining the temperature of the rail section. So, it is a bit faster arrangements. The maximum and the minimum rail temperature for a continuous period of at least 5 years shall be ascertained, and the mean rail temperature for the region arrived at. That means, if you are talking about Tm, which is a mean or the average rail temperature, then for this we need to have a data of 5 years. And based on that data of 5 years of the maximum and the minimum values of the rail temperature, we arrive at this mean value. So, this is a prerequisite so as to get the value of Tm. Now, let us talk about the thermal forces, and before going into the thermal forces, let us look at some of the definitions here. The first one is an anchor length. Anchor length is the length of the track which is required to resist the pull exerted on rails by the rail tensor at a temperature Tp. So, we have the rail tensors. This is one another thing which is coming up now, and these rail tensors are being used at the time of de-stressing of the rail sections, and the temperature Tp create an just resistance to the pull which is going to be there because of the change in the temperature. So, this length of the track is defined as the anchor length which is trying to resist it. And breathing length, it is a length of each end of the LWR or the CWR which is subjective to expansion and contraction on account of the temperature variation. That means, this is a length which is going to further move. So, these two things are correlated. Now, here when you talk about this anchor length LA, this anchor length LA, it is 2.5 meters per degree centigrade of a difference of TA and TP if you are talking about a broad gauge track which is being provided with 52 kg per meter rail section. So, for that case this can be calculated in this form, but for that we need those temperatures, the prevailing temperature and the actual temperature at the site. On the right hand side, what you can see is the temperature zones. So, there is a blue color, there is a yellow color, a light greenish color and the beige color. So, they are basically the temperature zones being depicted here. So, all of the country has been divided into these parts. So, that is the value, or that is the idea which you can take even from this diagram. There is a buffer rail, which is a set of rails which are provided at the ends of LWR CWR, which allows for the expansion or contraction of the breathing lengths, which happens due to the temperature variation. So, this is one another type of item which needs to be provided here. Now, rail temperatures for different zones, zone 1, 2, 3 and 4, which were shown previously in a country diagram also. So, in the case of zone 1, it is 40 to 50 degree centigrade, 51 to 60 degree centigrade is in zone 2. Then if we talk about zone 3, it is 61 to 70, and then it is 71 to 76 degree centigrade for zone 4. So, this is the range of the rail temperature which can be taken up. Then there is a mean temperature. We already talked about this mean temperature, which is an average which is taken over a period of 5 years. Installation temperature defined as Ti, which is an average rail temperature during the process of fastenings the rail to sleepers. So, when this fastening of the rail to sleeper is going on, at that point of a time, whatever is the temperature there is defined as an installation temperature. De-stressing temperature Td, this is an average rail temperature during the process of fastening the rails to the sleepers after making LWR stress free without the use of rail tensor. So, no rail tensor has been used. Without using those, using the rail free fastenings in that particular condition, then what are the temperature it is there, that is Td. If the rail tensor is used, then in that case that will be Td minus To, where To is the stress free temperature of the rail. Now, if we look at here in the case of the various temperature zones, the which of the rail section and what should be the range of the Td, they have been defined or given in this table. For the temperature zone 1, 2 and 3, all of the rail sections can be talked about, and here the value of Td, it ranges from Tm to Tm plus 5 degree centigrade. So, whatever is the mean temperature, to mean temperature plus 5 degree centigrade is the value which we can take. In the case of zone 4, there are two cases, one is 52 kg per meter and the heavier rail section, another is the rest of the rail sections which can be used. So, what it says, for the rest of the rail sections, it remains the same as we have talked about the zone 1, 2 and 3 for the all sections, that is Tm to Tm plus 5 degree centigrade, whereas for the heavier sections of the 52 kg per meter rail section, it is Tm plus 5 degree centigrade to Tm plus 10 degree centigrade. So, it is a bit further being taken. Now, what is prevailing rail temperature? The prevailing rail temperature is the rail temperature at the time of operation related to the track maintenance, and it is usually reported as Td plus minus x degree centigrade. That means, it is correlated with the de-stressing temperature plus minus x degree centigrade, and this x, this is a difference between the Td and the Tp, that is the prevailing temperature and the de-stressing temperature. So, that difference is being considered here as Td plus minus x degree centigrade. As I already said, the T0 is nothing but it is a stress free temperature, that means the rail temperature at which the rail is free of thermal stresses. Now, with variations in temperatures, the ends of the LWR and CWR moves, but the central portion remains as such, and that movement at the ends can be L into alpha into difference of the stress free temperature and the prevailing temperature. Now, when this movement is there, then there is going to be a building up of the thermal forces in the central portion. So, the last section is moving, maybe it is being contained by way of the use of the sleepers, by way of the ballast which is being placed at the bottom. This we have discussed previously too. So, there is a resistance which is offered by the fastenings of the rail with the sleepers and the combination of sleepers with the ballast, that also is going to put some resistance. So, the thermal force is calculated as E into A into alpha into T. Of course, units you can always look at, because it all depends how the values have been input there. So, here E is the modulus of elasticity of the rail section, and that is related to the material which is used here, that is the steel. The value is 2.15 into 10 raised to power 6 kg per centimeter square. A is the cross sectional area of the rail in the centimeter square units if we are taking. Then for a 60 kg rail section it is 76.86 centimeter square, whereas in the case of 52 kg rail section it is 66.15 centimeter square. Alpha is the coefficient of the linear expansion of the rail steel, and this is taken as 1.152 into 10 to the power minus 5 per degree centigrade. And T is the variation in the rail temperature with respect to Td or T0 or whatever the condition is there, accordingly we will take it. So, it is T0 minus Tp, or if we are talking about Td. So, that is way it will be taken. Now, say if we put the values here which are constant, say E is constant, alpha is a constant value, A is a constant value with respect to the rail section. So, if these values are being input in this equation, which is P is equals to E into A into alpha into T, and we do not have the T value here, what we are going to get for a 52 kg per meter rail section or a 60 kg per meter rail section is given on right hand side here, which says that it will be 1.608 tons per degree centigrade in the case of 52 kg per meter rail section, and it will be 1.868 tons per degree centigrade in the case of 60 kg per meter rail section. So, we need to know about the change in the temperature, and if you input that change in the temperature here, that means if suppose it is 30 degree centigrade or 25 degree centigrade, 50 degree centigrade, whatever is the value, if you just multiply with that value 1.608 into that or 1.868 into that, depending on 52 or 60 kg per meter rail section, you will get an idea about the thermal force P. So, let us look at this numerical here. We have a data E already known to us. E is 76.86 centimeter square. So, that is a 60 kg per meter rail section. Alpha is again known. The temperature, it is being defined, it is 30 degree centigrade above Td. So, we have to calculate what is the thermal force exerted here in this section. So, thermal force which is exerted is given by E into A into alpha into T. So, the multiplication of these 4 elements here. When we put the values of all these, that is E is 2.15 into 10 to the power 6, A is 76.86, alpha is 1.15 into 10 to the power minus 5, and the temperature change is being given as 30 degree centigrade. So, what we get is 57110 kgs or 57.11 tons. So, this is the total thermal force which is going to be exerted in that track. Now, let us discuss about the breathing length. Now, we already discussed that is a length which moves under the change in temperature. So, rail ends which moves longitudinally due to the temperature variations because of inadequate resisting forces offered by the rail and the ballast. That particular length is a breathing length. So, here if we talk in this particular section, see this is the total LWR maybe we are talking about, and that up to this point, this section or this section, there is a movement of the rail, and this movement of the rail is because of the change in the temperature, and because whatever the force which has got generated, it is not being resisted. The resistance will keep increasing as we move from the rail end towards the central portion because of the various types of fastenings or items which have been incorporated into the track, and they are putting the resistance to it. So, finally, a location will come where the two becomes equals, and after that there is a central portion which will be free of the movement. So, this expansion continues from the end of the rail towards the center, and it can be taken up as L into alpha into To minus Tp for the free rail condition, means the rail is free to move, then in that case it is alpha into L into the difference of the temperature. And there is going to be a stage where the resistance which is offered by the track structure will become equal to the thermal forces created due to the change in temperature. So, that is the position here, that the P becomes equals to R. So, this is the thermal force or stress, or this is the resistance being offered. So, when these two become equal, so then at that point it will stop, there will not be a movement further, a central portion remains the same. This resistance offered by the track structure is due to ballast, sleepers and fastenings. As per investigations, it is given that the sleeper ballast combination, it can resist the longitudinal force of 1 tons. The total value. So, if you have a sleeper being provided here like this, on the top of that the rail section will be there. So, in this case, so and the ballast is also being provided here. So, the resistance which is being offered by this is 1 tons in the longitudinal direction, and because you are talking about this and there is a movement of one rail. So, what happens is it is taken that as per the per rail seat it will become 0.5 tons. This will define the number of sleepers that would be required to balance the thermal forces. That means over the track. So, if we talk about the track, so what our number of sleepers we should have, which is providing this much amount of a resistance. So, this resistance R multiplied by the number of sleepers, that should be equals to P, and at that point then it will stop moving. So, the maximum movement at the end of the LWR is taken as m, and that is alpha into L into T divided by 2, or we can put the values of L, which is the breathing length, then it becomes A into alpha into T. So, alpha into T are again double. So, it means it becomes a square. So, A into alpha into T square of that divided by 2R. So, if you remember, that is the value of half of that value will come on one side. So, here you can see that overall arrangement is being shown of LWR. There is a certain portion in which the total force which has become equal to E into A into alpha into T, and there are the end portions on the either side which is having a breathing length, and beyond that only the SEJ has to be provided. It will not be in the breathing length area. The end sleepers will resist the thermal forces. The length over which the thermal forces will get balanced is the breathing length, and the gap in SEJ is adjusted with respect to the above conditions. Now, when Tp is equals to Td, that means the difference between the temperature, de-stressing temperature and the prevailing temperature is 0. In that case, the P will become 0, because it is nothing but E into A into alpha into T, where T is the difference between the prevailing and de-stressing. And the rail, it means rail is in a stress free condition. But when the Tp is greater than Td, then the P will be compressive in nature, and when the Tp is less than Td, then the thermal force here which is being created, which has got formed, is tensile in nature. Let us look at one of the numerical here. This is a numerical on the breathing length. The data is being given for E, A, that is the sectional area, alpha, the temperature difference. The sleeper spacings has been given as 65 centimeters, and the average restraining force per sleeper is defined as 300 kgs or 0.3 tons. We have to calculate the minimum theoretical length of the LWR beyond which the central portion remains free of the thermal expansion. So, the thermal force is P, which is E into A into alpha into T. We have the value of E, A, alpha as well as T. If I put those values here, what we get is 49152 kgs or 49.152 tons. So, these are the values which we get. So, P becomes equals to this. Now, we have the number of sleepers, and each sleeper is having certain resisting force. So, number of sleepers we can find out because we have this thermal force which is given is 49.152, and the resistance which is being offered by one of the sleeper is 0.3. So, if we divide 49.152 by 0.3, what we get is around 164. That means 164 sleepers are required. So, I am doing the same thing, that is N into the resistance per sleeper is equals to P. That is what we discussed previously. So, the approximate breathing length at each end of the sleeper spacing of 65 centimeter. Now, we have 164 sleepers being placed at a distance of 65 centimeters center to center. So, that means 164 into 0.65, 106.6 meters is going to be the length of the breathing section at each end. This is at an end, one particular end, and the total breathing length, which will be a summation of the breathing length on both of the ends, it will be 2 times of that, that means 213.2 meters. So, this is the value which will be moving. So, you have a track on this side 106 and you have a track on this side 106, it means the whole track is going to move. But if you have a track on 106 here and 106 here, and then in between some other track is also being provided as a part of it, then this will not be moving, only this and this will be moving. Another numerical we can see here, this is again a data being given as alpha, temperature variation is being given as 25 degrees centigrade. There is an elongation of rail due to the increase in temperature defined as 16.7 mm, and this is related with the rail end. So, at one of the end the movement is 16.7 mm. Calculate the breathing length of the rail end. So, the movement is defined as alpha into L into T. We have been given the value of the elongation. So, elongation value is 16.7 mm. So, it is being taken here. We have to find out the length L. Alpha is known to us and temperature is known to us. So, when we put all of these values, what we get is 57.98 or 58 meters. So, this is the breathing length at one of the rail end, because the data is been given with respect to that. If it has been asked that the data is being given for rail end for the elongation, but we have to find out the breathing length of the whole rail, then this would have been into 2. Let us look at one of another example here. Again, this is alpha being given, temperature rise is given, elongation is given in the rail. It is not rail end here. Now, it is in the whole rail, which is 33.4 mm. You have to calculate the breathing length of the rail. So, again the same formula will be used. Movement is equals to L into alpha into T. So, what we get is the value of movement, the value of alpha and the value of T. We have to find out this value of L, and this comes out to be 96.6 meters. So, this 96.6 meters is for the whole rail, and if we divide it by 2, then it is going to be the breathing length at one rail end. So, that is how the various values can be calculated if you have any numerical related to the breathing length. Here the values are being given of the breathing lengths for different conditions like the temperature zones, the various sleeper densities which can be used. So, 1540 and the 1660 are the two sleeper densities which are usually used, and then for a 60 kg per meter and 52 kg per meter rail section, the breathing lengths are being given in meters. So, in the case of 52, if you are talking about say the temperature zone 1 with the sleeper density of 1540, it is 52, but in the case of 60 it is 60, and then the rest of the values are again being given for that. So, a tentative value can also be taken from this table. So, now we will close our discussion today. What we have discussed is the LWR and CWR provisions, specifically on bridges, with respect to SEJs, with respect to piers and abutments, the measurement of the rail temperatures, the various definitions related to the rail temperatures. We tried to understand the thermal forces and the effect of thermal forces in terms of the breathing lengths. The other things which are left like consolidation of the track, ballast resistances, hysteresis, which we are supposed to cover in this lecture, we will be taking up in the next lecture. Thank you and bye.